Hello, everyone. My name is Nahuel Mirón Granese. I'm a postdoc at the University of La Plata, and I'm also working at the University of Buenos Aires. My postdoc is funded by CONICET. Thank you very much to the organizer for the opportunity, and today we will talk about the impact of self-interacting radiation on the primordial modes of the CMB polarization. Let me start with an observation that, in the words of Michael Turner, is the past 50 years has seen cosmology go from a field known for the error bars being in the exponents to precision sign. Basically, in 20 years, we passed from this to this, and from this to this. So in the precision cosmology era, we have two parts: the increasingly accurate knowledge of the cosmological observables, but we also have it is mandatory to develop our models with the dominant, but also with the subdominant or perturbative phenomena. Because in order to compare with observation, we need both the dominant and subdominant phenomena. So in this way, we have a major project in which we're working. Let me tell you about it. We want to describe non-ideal and non-equilibrium properties of matter, mainly during the early universe, and find the imprints of this phenomenon in the cosmological larger-scale fields we observe today. One example is the effects on the primordial gravitational field. We have two works in this topic. We have the primordial magnetic field, in which we have a work related to the primordial instabilities of magnetized primordial plasma, and the work that it will appear soon related to cosmic microwave background that we will talk about today. So this project is a joint project with Claudia Coccola from the University of Chile, Esteban Calceta from CONICET and the University of Buenos Aires, Argentina, and Alejandra Candus from the Universidad Estadual de Santa Cruz, Brazil. So coming back to the impact of self-interacting radiation on primordial modes, let me start with the first question and ideas that we had at the beginning of this project. We know that during the early universe, particularly before recombination, there is an interplay between the primordial gravitational waves emitted during inflation and the ultra-relativistic species, free-stream and non-interacting ultra-relativistic species present in the primordial plasma, and the CMB B modes, or in general the CMB, but particularly the B modes, of the polarization of CMB. So this interplay produces a very particular pattern in the CMB polarization that we could observe today. And our question is, what happens if we include interactions in the ultra-relativistic sector of the primordial plasma? The primordial gravitational wave spectrum will be the same. We don't know. The B modes spectrum will be the same. We don't know. And finally, if we can say something about the estimation of the tensor-to-scalar ratio today. So let me start with being more specific. We know that from inflation we have primordial gravitational waves. That's what the models of inflation say to us. And if we consider the Thomson scattering during recombination, we know, as I said, that we will have some primordial B modes. The evolution of the gravitational waves are determined by the transverse and traceless projection of the spatial part of the Einstein equation, and particularly the right-hand side is related to what we call the anisotropic stress, and it is the TT projection of the energy momentum tensor of the content of the universe. For an ideal fluid is vanishing, but for weakly interacting or decoupled ultra-relativistic species, we have a non-vanishing isotropic stress. So the game is as follows: if we have an isotropic stress, it affects the gravitational waves, and the gravitational waves could affect the primordial B modes. So what happens with the ultra-relativistic species in the primordial plasma? So we consider thermally produced ultra-relativistic species, and we have basically two components. Neutrinos, we're considering, of course, non-photonic radiation, non-photonic ultra-relativistic species. And so we have neutrinos, and we have dark radiation. Neutrinos, the abundance of neutrinos is related to this parameter n effective nu, And the interactions in neutrinos are determined by the rate of interaction this gamma. The abundance of dark radiation is basically this parameter delta and effective, and the interactions within the dark radiation sector are related to gamma, the DR. So usually we assume that both the whole ultra-relativistic sector is completely decoupled, and we have this bounds for neutrinos and standard neutrinos, sorry, and dark radiation. But now we want to study effects on the spectra of the primordial gravitational waves and of the CND polarization events due to interactions within the DR dark radiation sector. So schematically, we have, if we introduce interactions, then what happened with the variations on the primordial gravitational wave spectrum, and what happens with the variations of the V-modes angular spectrum of this in the polarization. And finally, can we say something about the tensor-to-scalar ratio estimation? So, okay, let me talk about what kind of simple interactions we're able to introduce. Here we have a lot of kind of interactions, but we will focus on this one, on the recoupling type of interaction, in which we can consider an action-like particle, a light particle with self-interacting lambda phi 4 interaction type. In this case, the gamma dr, the rate of interaction, scales as 1 over a. So that means that the importance of that interactions are more important for the late universe than from the early universe. So we keep this in mind because that's the model that we will use later on. So what are the constraints that we can have on these models? Okay, if we consider neutrinos, then we basically need to assume that they are free-streaming particles because they are tightly constrained by Planck and VO. So we directly go to the dark radiation sector, and there we know that the parameters of interactions are poorly constrained, and the major constraint is on the abundance delta and effective, as we see here. If we consider the model that I said, basically a self-interacting light action like particle with a Lagrangian interaction with a lambda phi 4 term, then we will obtain, as I said, some interaction rate, which scales as 1 over a. And this means that we can define some moving rate of interaction, which is constant and related to these parameters. Or we will call this 1 over tau. So this would be basically the frequency, co-moving frequency of interaction. So here we see that this parameter related to the amplitude of interaction is basically not constrained. There are some transitions and peaky features, but it is basically not constrained. So how do we introduce these interactions in the DR sector? Well, as always, we have the Boltzmann equation and the collision integral, and we will take the approximation of relaxation time for the collision integral. And if we perform a Legendre expansion of the tensor modes of the DR species, we will have this new terms in the hierarchy, the Boltzmann hierarchy, related to the relaxation time approximation of the collision. Then we will have all the coupled perturbations, and this sector is the ultra-relativistic, related to ultra-relativistic species. So we will introduce here the interactions, and then they will propagate through this hierarchy, this scheme that couples all the perturbations. So let me talk about the results. What are the impact of the dark radiation interactions on the primordial gravitational wave spectrum? Well, we know the dynamics of the primordial gravitational wave spectrum. We know the Einstein equation, and so we can compute the evolution of this spectrum. Basically, we know here viscous effect means collisional effect, but this is what the same as considering interactions. So basically, what we see is that we have obtained two regimes But the important thing is that there is a relative difference between the spectra with interactions and with no interactions. So we can quantify that effect. Here we see that if we consider delta N effective, the amount of degradation from 0.5 to 0.1, then the relative difference in the gravitational wave spectrum goes from 10% to 2%. So there is an actual change if we consider interactions. Then what are the impact of the radiation interactions on the primordial modes? Well, for this, we need to implement the equations that we showed before in a Boltzmann solver. In this case, it was class. And we include the dark radiation interaction of the slides of interacting action-like particles. And then we compute the different CLBB, which is the angular spectrum of the primordial modes, for different parameters of the interaction that we see here. This tau is what we call the inverse of the frequency, commuting frequency of the rate of interaction. So in this case, we have delta N effective equal to 0.5. And we see that we obtain different spectra for different, for a wide range of tau. So on the other, this is the same plot, but computed with the relative difference. And in this case, we can see and we can quantify that for a wide range of tau, of this parameter related to interaction, we know that basically the change in the relative change in the angular spectrum of B modes is of the order of 5 to 1%, depending on the delta NF and effective that we consider. So we can continue to the how can we analyze. We answered the two questions that we have. First, yes, the primordial gravitational wave spectrum changes, and the primordial B modes angular spectrum also changes. So now we want to study the estimation of the the estimation of the tensor-to-scalar ratio. So how can we analyze the impact of these interactions in this case? Well, we do not have, of course, we don't have data for the B modes because we don't have positive detection, but we can simulate observational data with an input model, and we can add noise, instrumental noise in sample variance, and then on the other hand, have a fitted model with some parameter. In this case, the parameter will be the tensor-to-scalar ratio. And then after a Markov chain, Monte Carlo Markov chain procedure, we obtain one best fit parameter that we call R estimated per noise realization. So with 100 realization of the noise, we can estimate the distribution of this variable, in which R estimated is what I said before here, and the R actual is the real R in the input model. So we construct data with an input model, and then we try to fit the parameter with another model in principle. So we will have different types of simulations. We have the check STD, in which the input model and the fitting model are the same, and the standard with no dark radiation interactions. We have another check, in which we have the int and consistency check, in which both the input and fitting model are the same. We have the case of interest, in which suppose that the universe have these interactions, but we are considering that the model of the nature is the standard with no dark radiation interaction. So if here, in this case, we obtain some bias in this parameter, then we can estimate, we can say, okay, this could be important. And then we have a control case in which it's just taking an input model as a standard, but then extract an effect that was included in the Boltzmann solvers since 2004, which is the gravitational wave sort, the anisotropic strength, and see what happens in this case to control the the amount of bias that we get. So here we have the result. These are the distributions of the variable delta R over R, estimated with 100 realizations per each simulation and per each value of R. So in this case, for example, for this value of R, we simulate the four type of simulations here. And these are the consistency check. Since the input and output, the input and the feeding mode are the same, we will expect no bias here. So we expect that the mean values or the mode of these distributions are 0. But here, the control case, we observe a very big bias. And for the case of interest, in which we consider that the real universe have interactions, but then we are fitting with a model that cannot consider those interactions, we see that the estimation of R have a bias. So if we see this plot in this case, which is basically the same as before, but just the three first simulation type, we observe that we have some bias for the green distribution. And one thing that one can say is, okay, but this is a bias, but can we distinguish this bias from the noise, from the errors, or is it impossible to do? In order to answer that question, we have this plot in which here we have the bias. Well, it's the absolute value that basically it's the same, related to the case of interest, the control case that we know that there should be a bias, and the two consistency checks. And we see that for some R's, for example, for R greater than 0.003, the bias is higher than the typical noise or the typical variance. So the conclusion is that for this type of this kind of values of R, the self-interacting propagation can introduce a bias in the estimation of R, which may be significant given the sensitivity of the upcoming experiments. So this is the most important conclusion of this work. And let me finish with final comments. So to contrast the theory to high precision observational data is instead to construct models that include not only the dominant effects, but also the perturbative and non-ideal ones. For the case of DR, the retardation as a live action-like particle with a lambda 5/4 self-interaction, the observations of the temperature and the E-mode's polarization of the CMB give a restricted bound on the abundance of delta and F, but the parameters of interaction are fully constrained. So for this model with delta impacted from 0.5 to 0.1, the relative variations of the spectra of the primordial gravitational waves and of the remotes, CMB remote, are of the order of 10 to 1%. The final amplitude of the effect on the primordial remotes depends on both the abundance of third radiation and the rate of interaction. But finally, what's important is that the self-interacting third radiation can introduce a bias in the estimation of the tensor-to-scalar ratio, which may be significant, as I said, given the sensitivity of upcoming experiments. So it could be important to consider this effect when computing R for the upcoming generation of CMB experiment. So let me finish with some of the questions that we can discuss at some point at the conference. The first one is, could it be possible to constrain interactions in case of a possible detection of the CMB polarization primordial mode with this analysis? Can this analysis be applied to massive particles, particularly to the whole dark sector, not just dark radiation, but matter and radiation? And can we apply this kind of analysis to other periods related to the early universe, such as reheating or phase transition? And the last point is, can we include these interactions or some effective models in the lattice codes used in cosmology, in particular the early universe, such as cosmologies like EC, etc. So, well, thank you for watching. See you at the conference. Bye-bye.